sure we'll have some people popping on as we get started here. I know for those out on the West Coast, it's a little early in the afternoon, so that might be problematic, but let me double check and make sure we're recording. Yes, we are recording. So this will be available if you have anyone in NAFEX, that's missed it. They'll be able to catch it, and people have been doing that. So if they can't make it in person, they've been going back and watching these online. So tonight we're gonna have Shannon. I'm gonna mess this up. Sorry. I can't even. I'm not even gonna try.
Mutschelknaus.
Mutschelknaus. Okay.
Yeah, that's pretty good.
Yeah.
Probably better than me.
And I'm German. I should be better at this. He's going to talk about passive solar, greenhouses, and a project I think he worked on with SARE as part of a SARE grant. And when we talked about this last week, the thought was he would kind of give a general talk, but he can definitely dive into specifics. So as we go along or after the end, if you want to get into some specifics with him, he's an engineer, and I'm sure having a husband who's an engineer would love to get into the nerdy side of things. So with that, I will turn it over to Shannon. And Shannon, I think you can share your screen whenever you want. I suggest everybody mute themselves and perhaps take yourself off of video. That will enhance your streaming. It'll be a better streaming situation for you.
Let's see if I can get the right screen shared. Oh, look at that. I think I do. Can you guys see the starting slide?
Yes.
Okay, good. I've got 3 monitors here, so
okay.
It can be confusing when sharing. And I'm not super familiar with Zoom, so. Okay. All right, so I ended up with kind of a lot of slides, so if it gets a little bit long, we can just hurry along. But like Chris mentioned, maybe a little bit of this will be a bit technical, but I threw in lots of plant pictures at the end. So if you're bored with the technical engineering stuff, hold on, there's going to be some plants too. So yeah, so this here's kind of a summary of some of the project, and go into a little bit of background too on passive solar greenhouses, because I don't know, maybe what everybody's background is with NAFEX here. So I'll start out with a little bit of that. My name is Shannon Mutschelknaus. I'm an engineer, but on the side I run a small farm called Wayward Springs. We raise, I guess you can kind of see in the picture, we've got beef, sheep, we've got the greenhouse stuff, and fruit trees. So for our presentation, I'll just talk a little bit about me and my farm, talk about what are passive solar greenhouses, for folks that haven't seen those, talk a little bit about fully passive systems, mostly passive systems, and then I'll talk about my prototype and some of the analysis I did before building it, and then a brief review of some of the performance data from 2020. And then I'll cover some of the stuff that we have or are growing in there. So a little bit about me. I'm a mechanical engineer. I've been designing thermal systems, research and testing of electronics for 20 years. One of the products that we make is these really large video displays. The Super Bowl was coming up, so I picked that one to throw on the screen as one of the products that we make. So this is a Raymond James Stadium in Tampa, Florida. And I also have a small farm. We have Scottish Highland beef that we raise. We raise Jacob sheep for fiber, meat, and for breeding. And then I've got a bunch of fruit trees and greenhouse technology that I work on. So maybe the specific research project here is part of a SARE research grant, Farmer Rancher Research Grant. And my objective was to produce data regarding the design trade-offs of passive solar greenhouse features, and then as well as demonstrate a selected design. I've found that the information out there on this topic is very poor. There's a few research papers. A lot of them are pretty dated, or a lot of folks have kind of run into issues with data collection, and don't maybe get everything accomplished that they want to with their projects, because it's actually fairly complex. I guess my motivation, I live in South Dakota, which isn't in the South. Many folks get that confused if you're not familiar with all of the states. We're in the north, it's fairly cold. Objective is to allow year-round crop production. Regular greenhouses make it pretty costly for a lot of tropical produce. We do have some folks in the area that do raise tomatoes almost year-round, and that takes a lot of fossil fuels to do something like that. So it's kind of my objective to really enable people to grow almost anything they might want in our climate. So if you wanted to look up more on that, I've got the research grant number there too. This is a 2-year project, which the final report and stuff will be done at the end of February. So that's not actually out there yet. But I do have like my halfway point kind of poster presentation I did last February at the Moses conference in person, just pre-COVID, before things fell apart. So that was in the link that Chris sent out. So if you haven't, you can check that out sometime. But that's also probably what you'll find if you look up this number at this point. So what are passive solar greenhouses? So as I kind of define it as a good passive solar greenhouse design is designed to minimize your total cost of ownership of the structure. That includes the construction of building it, the operation of it, as well as maintenance. In our climate, heating with propane is definitely adds a lot of cost to year-round growing. So the objective with passive solar greenhouses is to minimize or eliminate traditional fossil fuels for heat. So I put together some of this presentation was more for a local South Dakota Master Gardeners program. So I have a bunch of South Dakota stuff in here. And if we had Jorge or other Floridians, I thought I'd throw in this flag. This is the South Dakota flag. We're the Sunshine State, or at least we were back until 1992. But due to confusion with Florida, South Dakota was renamed the Rushmore State. So anyway, that does speak to the fact that we have a lot of sunshine, even though we don't necessarily have heat. So what are passive solar greenhouses? What do they look like? Here's a variety of different ones. Let's see if I can turn on the pointer. You can point to them. Okay, yeah. So starting on the top left up here, this is what's called a deep winter greenhouse. They call it a DWG. If you want to find information on these, you can Google search for that. This is a research project that the University of Minnesota has been spearheading for a few years now. This is kind of a standardized design. They've got all of the plans and information are out there for folks that you can have download for free. It's intended really for not for year-round growing, but only for the winter and or shoulder seasons. So it's designed. The architect that works on this, he refers to it as the F1, the Formula One racer of greenhouses. It's really designed for its exact purpose. It isn't maybe a great multi-purpose design, but it's very good for if you want to grow cool season produce in the wintertime. A lot of the folks that are using this are growing leafy greens, kale, other kinds of brassicas and things like that. And the reason it's maybe not year-round is the ventilation is just not sufficient for summertime. It gets extremely hot in these things. So that's kind of a summary on that guy. This is maybe another kind of design you'll see out there. Folks will do these dome structures. They look really awesome. They're not necessarily very efficiently designed, but they're a great maybe a marketing point there. This one is in South Dakota, in Mission, South Dakota. Another very common design here is what's called the Chinese solar greenhouse. I'll have a few more slides on that, but these cover many thousands, maybe millions of acres in China. And a few other designs out there. I just have the name on those two. It's pretty common. Folks would like to attach these to existing structures that they have, maybe a shed, a garage, or sometimes your home. And if you do attach them to like a home or some structure like that, you got to be really careful because humidity will become an issue really fast. And then this here is another design. I don't know if this is really a great picture. This is in Nebraska, the North Platte River District. This is, if you've watched many videos on this topic, you'd probably come across a fellow that publishes like Citrus in the Snow. It's a partially subterranean design, but yet has kind of a dome structure, maybe not too much different than the Chinese solar greenhouse, but it is partially set in the ground and is based kind of out of Nebraska. So that's kind of just an overview of what some of the range of structures are like. There's really a lot of stuff out there, and there's maybe a lot of confusion too on like what's a good design for what application. But one of the key features that really all of those have in common is that the south-facing surfaces have a transparent glazing on them, and the north-facing structures are opaque and insulated. And that's really because in the wintertime is when we really have low amounts of light and the sun is very low in the southern horizon. And so you want to make sure you capture all of that, both for heat, but also for light for growing. And then in the summertime, our days are very, very long, and the sun is actually a little bit more overhead and a little bit more from the north. And so having an opaque structure will help provide some amount of shading, as well as in the wintertime, you're avoiding heat loss from areas that you don't want to, that really don't benefit from having any glazing material. This is my structure. I think this was just a few weeks ago in one of our snowstorms right afterwards. So the question is, could it be possible to heat with only the sun in our location for year-round growing? So I have on the left here a map of our this is actually PV for photovoltaics, is really where you find most of the data for this stuff on. A map showing the amount of solar radiation that you get per day per meter squared in January. And you'd see that in our location, South Dakota, we get quite a bit of sunshine on average, not so far off from parts of California and maybe Alabama, Georgia here in our wintertime, which is interesting. So it would be awesome if it was possible to grow the same kind of things that you guys do in California and or Florida, the other sunshine state. However, our temperatures are pretty low. So this here's also a map from January of the average temperatures from 2018. And you see South Dakota here is fairly cold, other than North Dakota, parts of Minnesota and Montana. the coldest regions in the continental U.S. and maybe competing a bit with parts of Alaska. So what if we could take that extra solar sunlight that we get on our winter days and store it and use it for when it's cold out, or when it's nighttime? That's really the objective of, I'd say, my projects, to improve the techniques and methods for doing that. I don't know, maybe ask if anyone has any questions so far.
If anyone does, you can unmute yourselves.
My question is just the word passive. Why passive as a descriptor of what you're doing?
Yeah, that's a good question. I'll maybe cover that a little bit more, but passive is typically means to the fact that it doesn't consume any outside energy. You don't have to put any other energy into the system. So you don't maybe have to use propane to heat it. You maybe don't have to use any electricity to do anything. It all is energy from within its own system. Mm-hmm.
Are you going to talk about storage devices now?
Yeah, so next I'm going to talk about some of the aspects that you need to take into consideration when you want to select a site to install one of these. So that's maybe the next thing here, and then I'll break it down into passive methods of storing heat, and then I would say almost passive methods. So one of the key things that you need to look into when you're looking at building one of these is making sure that, particularly in the winter time, you're going to have a good, clear direction where you can get towards the sun. So this year's actually is from my site using an app called the Sun Position app. It's a free app you can download on your phone, and it's kind of magical nowadays, all the apps and what they can do. But it'll overlay the path of the sun for you on that day, and so you can check and see what kind of things might be obstructions. It worked really nice. If you're using the free version, a note is that it's only lets you do that for the day that you're out there taking pictures. If you buy the couple dollar version of it, you can set it to any day of the year, and check out your site situation and select a good location to put your structure. So in my situation, this was November 24th is when I was putting this together for the presentation. So actually by December 22nd, when that comes around, it's winter solstice. The sun actually would be a little bit lower in the southern horizon. This is basically looking straight south. So I had a lot more trees here actually that I took out. Lots of green ash and box elder trees, kind of a shelter belt of stuff. But in South Dakota, we usually don't have a lot of trees for obstruction, so it's not too big of a deal.
So Shannon,
Mm-hmm.
Somebody asked in the chat, what does the one orange sun icon represent on your picture?
Yeah, that's where the sun was when I took the photo, actually. Yeah, okay. So yeah, it was so cloudy that day, which actually why I chose that day was because then the sun doesn't like glare out the photos. So you can't actually see the real sun, but yeah, that's where the sun's at. I've trimmed out a lot of slides in this. I have other stuff about like orientation of the greenhouse and stuff like that, but to keep this under an hour, try to trim out some of that stuff. So fully passive heat storage systems, they're usually generally pretty simple. This here is one of the more common ones. This is what's used, maybe the stereotypical Chinese solar greenhouse, where the north wall is a heat absorbing system or structure. In this case, it's a packed earth system that they do on the north wall, maybe a few feet, or sometimes it'll be a few feet of earth, and then they'll put in an insulation layer, and then maybe a berm or something on the north side. Of course, the pros, it's fairly easy and cheap. And maybe have a typo there. It's easy, cheap, and it's pretty durable. It's not going to wear out. The cons is, for our location, it doesn't store enough heat for our length of days or our length of nights. The other big system that you see a lot of people doing is the underground structure. And I see a lot of people that come across this and they're just thrilled because it makes a lot of sense. You could, we know it's warmer down in the ground. If we can do an underground greenhouse like this, we can keep it warmer. And that's true. One of the main terms for it's a wallopini. I'll touch on that a little bit more in the next slide. But basically uses the ground on all sides of it as a thermal mass to help reduce temperature swings. So maybe delving into it a little bit more to its background, it was originally designed for use in La Paz, Bolivia, which speaks to maybe the non-English name for it. Have La Paz is shown here on the map. You can kind of see where it is relative to the equator. The big pros is you get thermal storage all the way around your structure. But maybe the cons, you might have stability issues depending on what kind of soils you have in the area. There's definitely would be a safety risk if this isn't engineered safely that it could collapse. So your walls would need to be reinforced depending on your soil types. Depending on where you're at, you might have water problems. You need to make sure you have necessary drainage in that. And probably the biggest thing that makes it not suitable for everybody is in the wintertime, our sun is pretty low in the horizon. So for example, for us in December 22nd, the sun at its peak in the sky is 22 degrees above the horizon. And so it's like this, you can see basically the bottom part of your structure, maybe where your plants might be, they're going to be shaded and they're not going to get much light. So depending on what you're growing, if you're growing something that's tall, where all your leaves and stuff are higher up, you might be okay. But I see a lot of folks getting excited and then they plant lettuce on the ground and then it doesn't get any sunlight. So you got to be very careful with the subterranean structures and make sure you're taking into account your sun angles. So another really good design that's out there is the Chinese solar greenhouse. I just like this picture kind of shows. It's pretty popular. It covers a lot of area. China is the highest greenhouse-based vegetable production in the world. And the data that I could find is by 2010, China had 1.9 million acres under solar greenhouses, which is just a huge amount of area. But it is only 17% of their total square footage. And there's all kinds of great research papers out there looking at various aspects of these, from various types of thermal mass storage in the back wall to the types of lighting levels that you'll get in different areas of the greenhouse and all kinds of stuff like that. So if you're interested in that, definitely you can find a lot of papers out there on the topic. So maybe just looking kind of at the structure itself, some of the main elements is it has the glazing on the south wall. It has this thermal blanket that's retractable. So during the nighttime or when the sun's not out, that will descend over the glazing material, so you don't have nearly as much heat loss out of that. And then the north wall has a heat storage system. This here comes from this paper down here. I can check that if you want. And that consists of a corrugated galvanized steel sheet on the inside layer, a layer of sand, and then a barrier of plywood just to kind of keep it separate, with fiberglass insulation, and then another corrugated galvanized steel layer. But that's kind of a nice overview of the Chinese solar greenhouses and how the general structure is laid out. And because this is a fruit group, a lot of fruit trees are grown in these structures in China. This is an example of cherries. You can read up on this article if you want to learn more detail, but really China's gone from being a minor cherry producer to at least number 3rd in the world, maybe higher. The data's not that great out there. And they have over 2,500 acres of sweet cherries being grown in solar greenhouses. And they're really using them to fill the market gap between southern and northern hemisphere cherries so that they can have sweet cherries, fresh ones, year round. It's also a nice example, kind of see what the inside of the structures look like. This here's another example with peach trees. For us in South Dakota, I'm in zone 4, but kind of the colder part of that. We can grow peaches sometimes. You got to have the right site, and it's kind of on the edge. There's a couple varieties you can grow, like Contender is probably the most common one. Being able to grow peaches consistently would be awesome, because the quality of peaches we get in the store are not so great. So in China, they've got over 40,000 acres of low chill greenhouse peaches and nectarines growing in these kind of structures. And you can see this is during the summertime. They'll actually remove the glazing material, not needing it for the summertime. And then when the winter comes, when things get dormant, they can roll that glazing over, and then also use the insulated material that they can roll over the top. Probably partially it can be used to keep it warmer inside, but it also is going to help them prevent it from getting too hot, which can be another issue in the wintertime for us on a clear sunny day. So the Chinese solar greenhouses are probably kind of the pinnacle of what I would call fully passive greenhouses. And they're used in China pretty much between these two latitudes, 32 and 43 degrees north. So, could those work for us? Kind of have a map here laid out of United States. I was kind of a little bit South Dakota focused, but you can kind of see we're probably a good ways above that latitude there. So maybe an example, one of their colder regions here is Shenyang in this part of China right up here. And you kind of see their temperatures. Sorry, all my temperatures are in Fahrenheit. I know we have some normal people from Canada on, but I went with Fahrenheit for us Americans, so I apologize. So these are Shenyang's temperatures. Our temperatures in Brookings, South Dakota, here where I am, they're actually not a lot different. Our January averages, highs and lows, they're not too far off. We do tend to have periods that can be pretty extreme, and so I kind of highlighted this. Negative 41 is pretty extreme, but it's not uncommon for us to get temperatures every winter that are negative 20 to negative 25. So we do have more extremes than they have. So I think for a lot of crops we probably couldn't grow year round. You definitely could be successful with cold temperature crops like brassicas, like cauliflowers, cabbage, lettuces, things like that. And of course, if you're going fruit trees, a lot of them could do this well, because they'll go dormant in the wintertime, and that could be awesome. So that was pretty much everything I had on fully passive greenhouses. Any questions on those?
I had a question. If it's fully passive, then you're not counting whatever energy source is needed to unroll and re-roll the insulation layer twice a day?
Yeah, so in China, the energy for that would be humans typically. But you can get electronic systems to roll and unroll that. Yep.
So then you have to have electricity for your greenhouse.
Yeah, if you want to do it automatically. Yep.
Or you have to store the solar energy in some sort of device that allows you to use that as energy to roll and unroll.
Yeah, yeah.
Like there's any area for solar panels on those greenhouses?
Yeah, did that one have it? A lot of the pictures that you see, they do have solar panels on them. Yeah, these don't. But what they'll do is they'll have a solar panel array installed right above the insulating curtain roll right up here, and that could be used for fans. A lot of times you might need airflow, horizontal airflow, to reduce humidity and keep down fungus, stuff like that, and other pests. Or, if you're doing tomatoes, you might want that for pollination and things like that. So a lot of these will have solar panels added to them.
And do they actually get enough energy just from solar panels, for example, to run fans to get the air circulation? Because I've tried that on a much smaller scale, and I need a lot of solar panel if I'm going to run a fan, even like half a day.
Yep. I don't know. That's a good question. It's there's not a lot of maybe easy to find articles out there. Usually got to dig into research papers to get a lot of info on this, and things change a lot in China too, pretty fast. So they do have power lines running to these that you can see. I don't know what all they're using it for in there.
How is the heat stored in the sand? Is it direct radiation onto that?
Mm-hmm. Yeah, yep. So that's really the big barrier, right? Is how fast it can absorb the heat during the sunny part of the day, and then how fast it gives off that heat is all controlled by the thermal conductivity of that storage medium, of the sand or concrete or whichever method they use. There's a whole bunch of options.
Now, it's a vertical wall, and do they paint that black or do they paint it white for light reflection?
Usually when you're using it as thermal storage, they'll try to make it a dark color. Yeah. So, if you're in greenhouses where that's just an insulating wall, you usually want it to be white to reflect your light, usually a matte white to give you kind of a nice diffuse is the best option. But like mine, I actually have like an aluminized foil because that's reflective as well, but not quite as good. But I don't need to put another layer of white on to make it.
Shannon, do you have any guidance on the energy blankets and if they have? I see they're using sometimes straw mats and things like that, but do they have a product here that would be comparable and that large?
Yeah. Yep. That one is, that's the lower cost, and probably the first version was straw like that. The commercial designs now, they are they're basically like a tarp with a fluffy cotton layer in there. Actually, I've got a piece laying on the floor here. They're really simple. But there's definitely challenges for us in using them. One of the issues, of course, is snowfall. If it's unrolled when the snow falls on it, or if snow falls when it's up, you may need to remove that snow before you can actuate it up or down. That's the big issue that people run into from folks that I've seen, like in Canada, trying to use it. Or if it's not fully water sealed, water can get inside of it, freeze, and then it's definitely not going to roll. So I haven't really seen examples of these in the United States being used successfully. The dynamics economically in China are different. Having somebody go physically move snow every day isn't that expensive, but that's not necessarily something we can do here.
What about internal insulation, like an overhead garage door?
Yeah. Yes, there are definitely designs and ideas out there, basically where they'll put a secondary truss layer on the inside and a similar rolling mechanism that will unroll it on that inner truss work. Mhm. I don't have a picture in here of that, but there are designs out there like that.
Well, it's been around for small passive solar additions for 40 years. I don't know if there's large scale stuff out there or not.
Yeah, I haven't seen any examples of one installed in large scale, but I definitely have seen plans and folks working on it. Yeah, I have some slides on like the insulation value of different glazing materials. I think I pulled those out of here, but you know, the polyethylene, if you have a double-walled polyethylene where you fill the middle with air, I think is that like an R value of like 1.2, 1.25, the insulation level. The blankets themselves, from the quotes I've gotten from Chinese suppliers, they're usually about an R3. So if you can roll that over the top, you get a lot of insulation value. So then I guess I classified maybe mostly passive greenhouses. These are ones where you do have some energy input. Usually it's in the form of electricity for fans to help you store the heat faster and withdraw it faster. So there's really two main types of systems that I usually classify these into. The first one is direct use low-grade geothermal, or LGG. There's a lot of different names out there for all these things, and a lot of times I see folks are kind of getting them mixed and confused. But I'd classify this as low-grade geothermal, or also sometimes called earth tubes. So what you have is a greenhouse structure, and then you have an array of tubes, a lot of times outside of the greenhouse, that basically pull the heat from the ground that was stored there year-round, and pull that into the greenhouse structure to keep it warm during times when you need heating. And the other system would be a ground-based heat storage system, sometimes called a climate battery, or a ground air heat transfer system, or a ground earth transfer. I don't know. They're all a bunch of acronyms. But they usually have the tubes are below the structure, and it operates in a little bit different fashion that I'll go into in a little bit here. So for the low-grade geothermal, basically what happens is you have your tubes that are in an array outside of the structure. This here is an example of tubes being installed. And this here actually is another system. This is a picture from the Russ Finch design, where he basically puts all of the tubes all in the same trench. And usually air is only blown through these tubes when it calls for heat. So the cool air in the greenhouse blows through the ground and is returned back into the structure, basically at what the ground temperature is out where the tubes are installed. So it's very simple, but you do have to do digging and install these tubes. Usually the tubes are drain tile tubes. These are 4-inch tubes. Folks will use different sizes. So this is geothermal. That the source of the heat is the heat that's in the earth. Usually is the average annual air temperature of your region. So for my area where I live, our annual mean temperature is 45 degrees Fahrenheit. And our ground 30 feet down is pretty much a constant 45 degrees. So you see kind of throughout the United States here in this section, how that kind of changes. We get farther north, that ground temperature is lower. The system might not work as well for you. You wouldn't be able to heat as much. But 45 degrees is what that temperature is, 30 feet down. Obviously, these aren't dug down 30 feet. So if you're doing geothermal design, this here is kind of a nice graph to kind of see what those temperatures might be below the ground for you. So for my situation, 45 is the TM, the temperature mean right here is 45. And as you go down in the ground, the temperature starts off plus or minus 10 degrees from the mean, and it gets closer to the point where you're at 28, 24 feet down here. You're pretty much constant 45 degrees year round. But usually these tubes are dug down maybe 6 to 8 feet within that range. What you'd see at the beginning of the season in the fall, you'd actually be able to get 55 degrees of heating from that ground system if you're buried 6 feet down. But by the time spring comes around, the ground has cooled quite a bit, and you might be getting closer to just 35, which if you're trying to grow tomatoes or something, these temperatures aren't going to help you a lot. They might keep the plants alive, but you're not going to be getting produce. But if you're just trying to prevent freezing, you might be able to do it. Maybe. 35 is probably pushing it, but so that's kind of a little bit of basics of the low-grade geothermal, and kind of the temperature ranges you'll see off of that. I do have a local system that's not mine, that I do have temperature sensors on that I'm monitoring to see kind of how it changes throughout this winter. So that'd be exciting to get that data. So any questions on low-grade geothermal?
You had a place in, he said China has more greenhouse.
All right, so then
No,
the next...
Shannon, I just want to say I love that graph of the soil temper, the temperature, the digger, or the farther down you go, yeah, I had not seen that before, and I really like that. Thank you for including that.
Yeah. I was debating because it's kind of hard to just quickly read, but I think it's important because I find a lot of folks like, oh, I go below the ground, it's constant temperature. It's like, that's not the case. My water lines freeze some winters. They're 6 to 8 feet down. It's not constant. You got to go down 28, 30 feet, and that's digging a well. So that's a pretty serious endeavor to do something like that. I could mention too, there's other variations that are possible with this that are not direct use low-grade geothermal. So you can add in heat exchangers, or you can add in heat pumps. So in our region, heat pumps can be used for a lot of the year to heat your home and other structures, but eventually our air temperature outside falls too low, and a heat pump can't extract enough heat from the air to heat your home anymore. So what people can do is use the heat source of the ground with a low-grade geothermal system like that as the heat source for the heat pump, and heat with that. So you're not pulling in the super cold 20 below air temperature and trying to extract heat from that. You'll get a much more efficient heat pump system. So that's something I've seen some papers and research doing as well. But of course that adds cost because you're adding more complex devices and equipment that will eventually fail on you. Okay, so the other main system here is a climate and earth battery system, and I'll go into this a lot more because this is what I'm doing on my system, and the research I'm doing is kind of around this. So the difference here is the heat source is the sun. So what we see, even in the wintertime, we get too much heat in our greenhouses. So actually, before I had my system running in December, I would see temperatures of 120, 130 degrees on a clear day in the greenhouse, and that's not good for plants. It's definitely not good for me. But if you can capture that heat and store that somewhere, that's great because then you can withdraw that later. So how the climate or earth battery works is it takes that excess heat, it blows it through a grid of tubes, usually in the ground below the greenhouse, and then it has insulating walls buried below those tubes to hold that heat within the soil stored below your structure. So they're used for heating, but they're also used for a significant amount of cooling. So then when nighttime comes or cloudy days are there, then you can withdraw that heat from the ground that you stored to heat your structure. So that's maybe the differentiator between low-grade geothermal and a climate earth battery. Maybe something to note is that if you fully exhaust the heat that you stored in your climate battery, it then basically ends up functioning like low-grade geothermal does, where you have heat, if you can cool this below that if you suck below 45 degrees, for example, for me, if it gets below 45 degrees, I start to get heat conducting up from the ground below it to kind of maybe recharge it a little bit. So it does function still, even when you fully withdrawn the battery, but not as well as it will when you have energy banked, stored within it. So that's kind of the basics of those two most common passive systems. Any questions on the basics of those?
So for the blowing the air down into the tubes, how powerful of a system do you need for that?
Yeah, that's a good question. You have to size the fans based on the size of your tubes. And that is a pitfall that a lot of people will run into, where they might put in lengths of tubes that are too long or diameters of tubes that are too small. And then either you can't get a fan that can even push it, or you have to use a very expensive fan in order to pump that air through there. So I've definitely seen situations like that where there's even some YouTube videos of guys like, I got this cool thing, he's all pumped and gung-ho and gets it buried, and then finds out he can't push air through it because he made his tubes too long or too small.
So in your system, what's the power usage of your fan?
Yeah, well, I've got a lot of data on that, so we'll come back to that. But maybe, because I won't cover it later, on the this design here, these tubes, they might make them 50 to 90 feet long, and that's quite a lot of friction or static pressure for the fans to overcome. So you'll have to use a centrifugal blower, like a furnace blower or something, in order to push air through that. So those do tend to be energy hogs. They tend to be loud and things like that. So anytime you can keep the run of your tube shorter, that you can stay away from using a centrifugal blower and use an axial fan, which will be a little bit more energy efficient and quieter. But that's the kind of thing that you'll be using for systems like this, would be a furnace style blower of various sizes.
So Shannon, there was a question in the chat. Someone says, I've heard the term ambient earth temperature before, but not sure if it has a scientific meaning. It says, I see your information and it seems much more precise than what I heard before. Does ambient earth temperature mean anything precise?
Mm-hmm. Yeah, I think usually when people are using that term, they're probably trying to refer to that 30-foot down earth temperature. But a lot of times people will get confused and not realize that you need to go that deep to get to that temperature.
Okay.
Yeah, so now we'll go into more details on my system and what I've got going on. So it's kind of just the CAD model, kind of showing the guts of it. This is the outside. And it's got the south-facing glazing wall, and then the north wall is insulated. It's a 2x6 stud wall. took the design of the north wall, really was what the deep winter greenhouse structures were using at the time. Dan Handine actually has some new designs out just in the last few months for a farm scale version that I think has some insulated wall designs that I like better. But it's a 2x6 stud wall with rock wool insulation, which is a little bit better than fiberglass, but the key thing is that it's more moisture resistant, so it doesn't get nasty and mildewy. And then on the inside, I don't know if I have any inside pictures. I have polyisocyanate foam board on the inside, which has a metallized foil, which is a really good vapor barrier, so you don't get moisture permeating into that wall. Because if moisture does permeate into the wall, you lose your insulation value, as well as you've got mold and mildew issues. Yeah, so then the ground level here is right here, and it has a grid of tubes. Initially, when I installed it, I had tube intakes here. The fan is located at this location here. Blows into a little bit of a manifold, and it has a bunch of cross tubes blowing across to the side, and then it comes out over here. And I'll have maybe hopefully a little bit better illustrations of that. I also have passive intake and exhaust vents. So there's a set of doors here in the lower bottom, and a set of doors up here. And what I used when I put these together was actually they're just house style doors, because I thought it was easier than fabricating something myself. So they're like a R8 insulated door structure. And I kind of talked about the airflow direction already through the system. Maybe note for like the insulation here, I put 4-inch insulation with the short 2-foot frost skirt on the bottom of this. So this is overall the layout. Next, we'll talk about maybe more simulation stuff. Any questions about just the overall structure?
What's the structure, Dan, that's behind the greenhouse? Is it a shed or is it?
Well, it's just part of the greenhouse.
Yep. That's the insulated wall of the greenhouse. Mm-hmm. Yeah.
Very nice.
So part of my study was looking at and comparing different ways you could insulate the climate battery. One of the key things is when you store that heat, you want to make sure you don't lose it, but you don't want to spend an arm and a leg on insulation either. So I do have in the drawings and the models a poured concrete foundation. This is definitely not something you need to do, but I did it for building code purposes. In case I attach this to my house with a breezeway someday, it needs to be a similar foundation as the house structures. But if you're doing it totally separate, a lot of folks will just have pylons for the greenhouse that go below the frost line, and then just bury the insulation sheet directly without concrete there. But I guess in the image here, you can kind of see from the simulation, these lines here are what's called isotherms. These lines are where there's a constant temperature basically through the system. So in the illustration here I put in for this, the outside air temperature is 0 degrees Fahrenheit. And then the inside temperature of the structure is 70. So if you had 70 degrees of heat stored, this is what your temperature distribution would look like through the ground surrounding the structure. The equivalent R value from inside of the foundation outside to the air in a non-insulated structure would be an R value of 5.3. And then through the footing itself, because the distance is greater up to the air, would be around an R value of 15. the system that I ended up building with the insulation, ended up with an R value of 23 from the inside out, then 19 through the bottom of the foundation. So yeah, so these here are three different versions that you could do with different insulation levels. You could do 2-inch, 4-inch. I didn't want to go through all the details here because you guys might be bored, I'm not sure. But it's got little arrows, shows you basically the length of the arrow on each photo is comparable. So you can see the amount of heat that's transferring and where it's being lost. So you can see that once you insulate that foundation, most of your heat loss ends up being through that footing or from the ground, kind of wrapping around from the bottom of the storage system up to that. So then I did some comparisons of different ways to make a frost skirt. I know someone on the Facebook asked about frost skirts, and this third one here would be the stereotypical frost skirt design for homes. And the reason they're used in homes is in our northern regions, you want to make sure your foundation is dug deep enough so that when the ground freezes and thaws, your house structure doesn't go up and down with the freezing and thawing of the ground. So your foundation has to go down below the frost line. But that's expensive, and so sometimes you can get by with not digging as deep if you put in a frost skirt, because that will stop the bottom of your foundation from freezing. So you can put in a shallower foundation if you put in a frost skirt. So all you're trying to do in that situation is stop the bottom of your foundation from falling below 32 degrees, which is a little bit different than the objective here. I want to keep all of this heat that I've stored to withdraw it later. So really the area with the most effectiveness is if you can put that at the foundation where a lot of the heat is kind of wrapping around. Give it it's got to go kind of around this, basically. I did put a little red X here on the ones that I don't really think are good options for most situations. And these other ones are good options, but it really depends on how far north you are. So, the farther north you are, the colder your climate. You might want to look more at something like this. Or if you're in, Nebraska, maybe something more like this, and so on. But I'll put more specific guidelines to that in the final report when I get that done.
So Shannon, 2 questions in the chat. Someone asked, what is the square footage of your system?
Yeah, that's a good question. It's 16 foot by 28 foot.
Okay.
So it is that 448 or 450, somewhere around there, square feet.
Okay.
Don't ask me to convert to square meters.
And then Leslie asks, if you were attaching this to a garage, what measures, including additional measures, would you take to mitigate moisture?
Yeah, so it depends on if your garage is like a heated structure or a not heated structure. If it's a not heated structure, you're going to be less likely to get condensation in that wall because your garage on the other side will be cooler. But there's guidelines out there for that. You have to change which side of the wall you put your vapor barrier on. Your vapor barrier is supposed to be on the cold side or the warm side. I don't know. The answer to that is I don't know. But there are guidelines for doing that are different between a heated or an unheated structure. That's the key thing that drives where you put your moisture barriers. Was there any other questions? Okay.
That's all that was in the chat.
Okay. So then the heat exchanger system itself. I did a bunch of what's called CFD, computational fluid dynamics simulations, to look at some of the different things to do and to not do. And so this here is kind of a bottom view of, say, the grid of tubes. In my system here, the cross tubes are 4-inch because 4-inch is just so darn cheap. And then the manifold is 6-inch. I've seen the prices just go up a lot if you go above 6-inch. Maybe it's because I'm in the Midwest and you can buy these in huge, ginormous rolls to drain tile your field. So they're pretty available and cheap. But if you get much bigger than this, then you're starting to get into like culvert sizes. The costs go up a lot. So that's kind of why I picked those sizes to kind of optimize and see how well they performed. So the spacing in this design is 2-foot spacing. I didn't find a lot of info out there on this. This is really kind of one of the gaps of information is, what's the right spacing to put your tubes to make it effective. The closer you put them together, the more of your thermal mass you're displacing. So you don't have as much storage capacity, but the closer they are together, the faster you could transfer heat into it and the faster you could withdraw heat because you have more tubes in there. So in that array of tubes, one of the key things is you want to make sure your airflow to each leg of that tube is as equal as possible so that you're getting a uniform, effective heat transfer into the soil. So this example here shows kind of what that looks like. So if this is the tube coming in, you'll see that the coloring here is the velocity, the speed of the air through the tubes in inches per second. So you can see that this end one over here is getting more airflow, of course, than this one. But this is actually a pretty good, pretty even system for something that doesn't have any special additional features like baffles or some other kind of a constrictor you could put a smaller diameter tube, say on this guy, and that would reduce the airflow in this one and boost it in the others. But my objective was kind of to keep it as simple as possible and get it as uniform as possible. Yeah, other simulations I did too that we probably won't go into, but I'll show a few more images of different layouts. So my system has 2 layers of these tubes. This is the 4-foot down layer, and then I add a 2-foot layer of soil, and then another layer of tubes. So they're basically all spaced 2 foot apart, up and down and side to side. So looking at some different designs where you could do in the layout, the tube spacing here is still the same, but the intake into the manifold is coming in at a 90 degree. This is a reasonable way someone might want to build it because you can buy off-the-shelf fittings that are T-fittings, where you might be able to connect this guy right on there, pretty nice and elegant, it's not sticking out the end. But what you'll see happen is the air is coming in and it hits that tube, and the first tube in that line gets starved of air and actually wouldn't function much, if at all. So that's something you don't want to do. So maybe the next obvious thing is I took that and fixed that issue. And when you have a flow in from the end, you'll get airflow to all of them. But of course, you have this gradient across here. Reasonably good. But one thing I did do was change this end tube and reduce the length of the 6 foot and made a little bit longer run of the 6-inch and put a longer run of the 4-inch. And that adds a little bit more constriction to this end tube and gives you a little bit more even than the basic system. So that's what I'd say is maybe the most even flow you could get without adding any other sort of additional cost of other components.
So Shannon, there's a question from Dan. How do you deal with the mold from the condensation in the pipe?
Yeah, that's a good one because you get a lot of condensation, and I'll talk about the amount of condensation and heat that helps with later. But when you're using these tubes, you'd always want to make sure you're using the perforated drain tile tubes. So the moisture that condenses in these tubes will drain out those slots, those holes, so that it doesn't remain in them. In mine, the 6-inch and the 4-inch are all perforated, but if sometimes people will use like a PVC tube or something, and if you do that, you need to make sure that it's sloped so that any water that does condense in there will run out to a spot where it could drain out of the tube. As far as mold in the systems, even with this, there may be concerns. And the University of Minnesota guys have done air quality studies, and they found that the air coming out of the systems after a few years of age are still cleaner than the air going in as far as mold counts and things, which is interesting. And I guess I haven't done anything fancy like that kind of mold counts, but I would say that it doesn't ever smell bad. In fact, it smells nice and fresh. So, maybe it's that fairly continuous airflow probably is preventing some of that growth.
Shannon, have you found in your modeling an ideal airflow velocity through the tubing?
Yeah, that's a good question. I don't have graphs in here in this presentation on that, but when I selected my fans, I made sure that I had variable speed fans so that I could run them at different speeds and characterize how much heat transfer they could provide. So I do have data on that. That'll probably be in the final report, but I didn't put it in here.
Okay.
I'm not sure who asked that. Was that Tim?
That's
Yeah.
Tim.
Yeah. Yep. That's a good question. We can talk about that after the presentation sometime.
Yeah.
So does this thing work? That's maybe the question that I had, or how well does it work? It seems like it should do something. So that's maybe on the time thing here. So I just finished construction and got my wiring done for the fans actually on New Year's Day, January 1st, 2020. So all of my performance data starts there. And I guess I was just kind of looking at that 1 year data when we had our last NAFEX conference meeting. I was like, you're looking for things to present on. I was like, I could probably talk about this. So I've got 1 year of data, and we'll go through some of that. So this year's maybe just kind of a nice breakdown of some of the details, what happens on a day-to-day basis. This actually was in my conference poster that I had, because this is actually from February. And so this was nice because it had 2 adjacent days, one that was a cloudy but fairly warm day for us, and then it had a sunny day, but it was cold. So the top graph here shows the amount of solar radiation that was hitting the greenhouse structure of a meter that's south facing inside the structure, capturing this. So you can see the cloud cover was pretty cloudy, didn't get very bright. I had a maximum of 340 watts per meter squared solar radiation. Then the next day was more sunny. The green strip here is times when the fans kicked in to store heat. And the red band is time when the fans kicked in to withdraw heat from the battery system. So the greenhouse air temperature is shown here, and then our outdoor temperature. So pretty mild day for us. For February, it was 29 outside, and it cooled off a lot overnight. But it's actually ended up being our coldest night of the year. So minus 23. And you can see even on this cold day, the amount of solar radiation, it got probably too warm in there. Really, 98's a little bit warm for most plants, with a low of 38. So the fans, someone asked about current rating of the fans. I have 4 fans in this system because I have it split up into 4 different arrays and 1 fan on each. So this is the total amperage of all 4 fans when they're running 3.3 amps. Yeah, you just kind of see when they turn on, shut off. And then this is a measure of the sensible heat transfer through the system. So maybe for reference, it's 19,000 BTU per hour is our peak heat transfer down into the soil when it was storing. And then in the nighttime when it was heating, I was giving 7,000 BTU per hour. The energy to run the fans, of course, is not free. So I just kind of totaled up here what the total energy cost was for that day. So 20 cents and 77 cents. And then I compared that to the temperatures that we're heating it to and the outside temperatures, what a traditional greenhouse structure might be. So if you have a glass or a single layer of polyethylene, to keep at these same temperatures, you would have had to spend $5.40 of propane to heat that based on whatever our propane costs were at that time. And if you had a triple-walled polycarbonate structure, which is really what mine is, it would have cost you $2.11 to heat it to these levels that day. So it's pretty significant. On a day-by-day basis, it's not a huge number, but that adds up over the course of the full winter.
So Shannon, somebody asked, what are you using to record your data for this?
Data loggers. I have a variety of different data loggers. I'm measuring air temperature within the structure, a few different places. I have some solar radiation loggers. They're made by Onset, Hobo data loggers for the solar radiation. I haven't talked about it yet, but I have temperature sensors in the ground to measure the temperature of the soil. Those are thermocouples on fiberglass rods that you can pound down into the ground. The current sensor on the fans. Measuring airflow is I have a handheld anemometer for that. I don't measure that. I don't log that. The temperature sensors and current sensors are logging at a 10-minute interval. And some of them are a system produced by Monit, M-O-N-N-I-T. I selected them because it's kind of a cloud data storage system, and it allows you to access the temperature sensors via an app on your computer or on your phone and look at it any time. So that you can wake up in the middle of the night and check on your plant temperatures, make sure they're happy, and then you can roll over and go back to bed without walking outside. But not all the sensors are on that system, just the essential ones, because it costs more. I thought maybe it'd be nice to share some example data of a little bit later in the season. So in that February timeframe, you can see 98 is getting a bit hot. The battery wasn't able to absorb the full extent of that without it getting too hot. Most plants you don't want in that temperature range. So I have the upper doors are automatic with a thermostat and some linear actuators that open and close them as the thermostat calls for it. So you kind of see here during the nighttime, this is midnight here, 6 a.m. in the morning, you can see when the fans kick in to heat, I can see that little blip in the temperature down here where it kicks into heat, warms up, they shut off. And you see the humidity goes up and down with that as well. The climate battery does help with humidity control to some amount. So that's a nice thing. It's definitely better than if you had a fully passive system. There's a lot of issues with the Chinese solar greenhouse structures with too much humidity and condensation because they don't have any way to deal with that. So this when you're blowing the air through the ground, you're losing some of that moisture into the ground and reducing humidity a little bit. So then as the sun comes up, our air temperatures go up to the point where the climate battery kicks in again. You can see here I had to set at 75. That kicked in to store energy. Changes the slope of that temperature rise up until the point that I had the vent doors. I think I had them set probably at like 90, or I have just a thermostat I took out of my house when I remodeled that I put out there. So you can't get it set super precise. Probably actually 93 is probably what it's at. And you can see each time the doors open and close to let in some cool air. So it's kind of a neat graph because it just shows you all those kind of details in one day there. Any questions on that? Okay, so all of 2020. So I've got kind of two main lines on here. The dotted line is our outdoor, our average daily temperature is the dotted line, with the blue and the red being the maximum minimums for each day. And then the black line is the greenhouse. So I'll kind of go through some of these. The coldest point that I had was at a low of 29.1, which is below freezing. Now, when I started the system in January, I did not have any heat stored in the system because that's just when I first turned on the fans and had stuff operating. So I do expect that January, this is probably the lowest possible temperatures I should ever see without, I don't have any other source of heat because that would taint my data. But definitely a lot of folks would have some sort of backup. I guess my biggest fear is always kids play out there, they leave the door open. That could be a bad thing. But anyway, that was the lowest recorded temperature. Definitely this winter so far, I haven't gotten anywhere near that because I have heat stored from the summertime and in the fall. I just got the roof vents automated starting at this point. So you can see I had some days where I got above 100, which is too warm because I just didn't realize how much heat this thing would capture in the wintertime. And those roof vents really worked really well. I had it set to 90 and they were able to keep it pretty close to that for a lot of the summer. Out until really in late August here, I found that it was getting too warm for what I wanted. And then I ended up opening the bottom doors. So actually, probably one of the big things I'd suggest is, not to use the bottom doors. There's probably other alternatives like shade cloth. There are other things that are better than having this wall with these doors here. The wall has a negative effect of blocking some of your light during the wintertime. It's added complexity, but it also lets, if you don't have a screen on it, it lets in insects that you may or may not like. Most of them are the ones I didn't like, unfortunately, as well as mice or other critters that you don't want in there eating your insulation. So I think what I'd like to do in the future is use a shade cloth. You can buy those and 20% or 10% and really only using it for a short time of the year. It would last a long time. So then as it started to get cooler out, I had the heating thermostat set to 60, and you can kind of see here in the data, really I was able to maintain a bottom temperature of 60 all the way out here into, it was late October. When we had some cold spells coming, I was like, I probably shouldn't waste all my heat right away. So I set it down to 50, starting at this point here. And it really maintained 50 in there all the way out until mid-December here. And then I had to set it down to 45, which is what it's at currently. So that's kind of an overview of the temperatures inside for the year. The total operating cost of the fans for the whole year was $131 or 29 cents per square foot, which is pretty good. It actually ended up for me being a net reduction in electricity usage because I kept a lot of my plants in the house previously and had to use grow lights. So this is much cheaper than using grow lights. So looking into the thermal battery temperatures themselves, I have sensors at 2 locations, one in the middle, or actually I have 2 at different depths, but I have them in the middle, and then I picked along the south wall because that should be one of the coolest regions, whereas the middle should be the warmest. So I'd expect the temperature distribution in the wintertime to look something like this, with the cooler parts being outside where heat's being lost, with the warmest being in the middle. So the light gray line here is the 4-foot middle one, and the black one is along the south wall sensor. So I started off basically at what the geothermal guys would say my ground temperature should have been without having anything stored, at 45 degrees here. It's a little bit colder towards the outside of the structure. And our January actually last year was our record cloudiest January recorded. So that was nice for data capturing, maybe not for growing things, but it was good for seeing how poorly the system could perform, and kind of seeing the bottom end of that. You can kind of see how my net heat storage, of course, increased as our days get longer and our temperatures outside get warmer, up to probably a peak of like 73 degrees in the ground. I had some temperature sensor issues here where one died and had to replace it. And then, here at the end of the year, I ended up here with the center ones being at 52. And actually, I think it's been climbing back upwards now. I think today it was at like 54 or so. Into January, this would be ending kind of at New Year's. So this is looking at the top-down view of the temperature gradient. You see kind of during the first part of the year, there's really not much gradient when you're storing, but there ends up being an increasing gradient here in the withdrawal periods, probably because the outside ground is quite a bit colder than the inside ground. So you're seeing more heat loss going to the outside. Then at those same measurement points, I've got temperature sensors 2 foot down and 4 foot down. So there's maybe a side view of the tubes and where these sensors here are at. These here are the 2 along the south wall, so the coolest measurement points. And so one of the big things I was looking at was how well can the system cool during the summertime. And it really kind of trails off in the middle. But we also see that the top layer of tubes are warmer than the bottom layer of tubes, which makes sense in the summertime because the heat is conducting downwards, because the ground is 30 foot down is a constant 45 degrees. But we see that kind of flip once we get to the December timeframe here, where basically my temperature is getting pretty close to withdrawing all the heat from the battery. And it actually starts to function as a low-grade geothermal, where that heat below the system is starting to conduct upwards. So then we see that the lower 4 foot ground temperature tends to be above the upper 2 foot temp sensor. So, overall, the top layer of tubes can't do as much heat storage and cooling as the deeper 4 foot tubes can. So if you're looking at saving costs by doing just the top layer or something, you're not going to get as effective of a system with just the top layer of tubes. So the engineer in me is most excited about how much heat did we actually get stored in this thing and how much cooling did it actually provide. So this here is throughout the full year. The red bars here are the amount of heat extracted from the system, and the blue is the amount of heat stored or cooling power maybe that it was able to provide. And it's reasonable for something fully passive. It's not bad. So maybe kind of looking at the data in detail, when the ground below is pretty cool, it actually has quite a bit of cooling power and can absorb a lot of heat and really temper those hotter, sunnier days that you have. By the summertime, there's really it's not able to store nearly as much. So it definitely is not a sole source of cooling, and you need to have something else. And the amount of heat that you can extract is definitely much higher after you had more energy stored. You can see that overall I'm able to heat more by a far good bit than I could back here. Any questions overall on the total heat storage?
Shannon, are you banking heat during the summer, or are you letting it kind of passively warm up from the ground heat? Mm-hmm. Just the natural summer process of heating the ground.
Yeah, for this year, I did have it running in cooling mode when it would get above, maybe 75 or 80. I have like tomatoes and peppers and other things in there that are air pollinated. So the fans also help with the pollination of them. So I did want to have fans on anyway, some amount, and I wanted to capture the data, which you definitely wouldn't need to run them in the summertime if you didn't want to. But you can see through the summer here, it was putting this amount of heat into the ground.
Yeah. And do you have any sensors any lower than the 4 feet just to see how much is actually kind of migrating?
I don't. That would be interesting because it should be conducting down there a pretty good amount. So yeah, it would be interesting.
Since you used 4 fans, did you end up with the centrifugal fans or the axial fans?
They're axial fans. They're 8-inch diameter axial fans. I don't have any pictures in here, but they're kind of like an inline duct fan. Sometimes you can get them as like booster fans. You might be able to put in your house ducts and stuff like that.
And you said you used 2 for each of the layers. I know when you did your diagram of airflow through the layers, you had only 1 input tube and 1 output tube. So where do you have the 2 fans?
Yeah, I have of that array that I showed in the diagram. There's actually 2 of those on each layer side by side. So there's 4 arrays.
Oh, okay.
Yeah, it's kind of visible here in these images. See right here's one, and then there's another one right here, one right there. So there's 4. Yeah. One of the things that folks talk about a lot with these systems is you get 2 types of heat transfer. The first type is sensible heat transfer. Sensible heat transfer is basically you blow the air in and it comes out at that temperature at some, it's increased or went down. So it's just the energy that's required to heat the air, not taking into account any condensation or evaporation. So that's actually the easiest to measure and calculate. So this first graph up here is showing the sensible heat transfer through the system. The other type of heat transfer is what's called latent heat transfer. And this is the energy that's stored due to a phase change because the water vapor has either condensed or evaporated. So I kind of split those out. The other graph on the prior slide is actually the total. This is then broken out because I wanted to see, how big of a role is the humidity condensation playing. And one of the things that I've seen people say, maybe without any information or data on it, is you need to keep your tubes such and such length, or you won't get, the air won't be in there enough time to get condensation. And I can't say that these tubes with the length that I had, it appears I got pretty good condensation. Definitely, it helps with the cooling. It helps you cool much better because you'll get more stored because the water is condensing, going through a phase change there.
Are you doing anything special to try to get water to drain out of those tubes?
Nope, I don't have anything special. Sometimes folks will say you need to put like the socks on the tube so that like dirt and stuff doesn't wash into them. That's true, like if you're doing it for drain tile in the field because you're expecting a gush of water to go through these. But I don't have any sock on them, and most of the folks that I've talked to say it's not necessary either. The slits in them are so small that you're not going to get a lot of soil and sand or whatever going in into the tubes. It depends on your soil types. If you have like really heavy clay soil or your water table is pretty high and close to the tubes, you may need to have a sump pump or a drain tile below these. I've seen people that will do that where they'll have a actual drain tile to a sump pump below these so that they don't fill up with water. Actually, the other one locally that I was monitoring, that was their problem originally when they had it installed. They have really heavy clay soils, and we had a really rainy year the year before this, and the tubes fill up with water, and obviously when they're full of water, the air won't blow through them. So that's definitely an important thing to prepare for. My site is well drained. Actually, that picture I had a while back of the tubes, the day after I took that picture, we got 7 inches of rain, and the system drained. I don't. It's kind of miraculous actually, but there wasn't water in the foundation and stuff. I had lots of toads living in there, but not water.
Do you have any experience with the types of fans that they use for radon remediation systems? They're like a big pancake, but on 4-inch in and out. Are they are they a centrifugal type of fan in there? I've never seen the insides.
They're usually an actual fan. There's some of them they're kind of a mixture actually between them. The blades are just at a little different angle. But they're usually very low airflow because they're just pulling a little bit of air out. It's you could think of these are like similar to that, but they're 8-inch diameter and higher airflow.
It's not a high static pressure fan. Then it's just enough to keep negative air pressure on the intake side.
Yeah. Yep. These. Trying to think. I think like they're 400 CFM, something like that. I haven't gotten through that data recently again, but of course that info all plays into the calculations for your heat transfer. So you do need to know your airflow. Now, one of the biggest pitfalls I see folks having with fans is they'll read that spec on the fan and say it's a 500 CFM fan, and they'll think, oh, I'll put this 500 CFM fan in this thing, and I'm going to get 500 CFM out of it. And that's not the case. That's that's the measured airflow with it not connected to anything, with no back pressure. So you'll want to make sure you look at the actual fan curve for the system, or for the fan and for your system, and you want to look at where those overlap. That could be a whole nother presentation because that's kind of fun too. But usually if you don't know how to do those calculations, you don't have that information, it's safe to assume that your actual airflow will be half of what that rated open air CFM spec is.
What's the specific heat of wet earth or moist earth?
Yeah. So the amount of heat that you can store changes based on the soil types that you have, and maybe even more so the amount of moisture in the ground. For me, I am growing in the ground, so I do water the plants, and that does keep the soil moist. It's a difference of about 25% for a specific heat change from whether it's wet or dry.
You know what the range is? I think like rock is about 0.25 and water is 1.
Yeah. I don't know it off the top of my head. I had some slides on that, but I took them out. I'm sorry. Maybe if we do another more detailed presentation sometime.
How much carryover are you getting from summer to winter, do you think?
Of the heat?
Yeah.
Yeah. Well, that's really what's kind of looking at with these ground temperatures. And what I've found is I can probably extract it faster than I can consume it if I'm not careful. So I really wanted to see how warm I could keep it as long as I could. So I probably kept it higher than I needed to, and I was keeping it at 60 and keeping it at 50. I have some true tropicals out there, like durian, if anyone's familiar with what that is, and that takes damage below 60. So I had my thermostat set at 60 to keep that guy warm enough, and then brought it in when I set stuff below 60. But if you were to set the thermostats lower in the fall, it would carry over longer.
So Shannon, somebody asked, I know you've mentioned tomato and I think peppers and durian. What are the other plants that you might be growing in your structure?
That's a great topic to cover because it's more exciting. It's why you might do all this work. So I have a few slides on that. How are we doing on time? Is it okay?
People can stay on as long as they want. I mean, we're past 8, but we'll just keep going as long as people want to ask questions. And
all right. I know someone talked about black sapote before we even started, so I've got to make sure we get to that. So I'm doing a slide here of tomatoes. I guess one thing that I've really learned a lot about is growing vegetables that I thought were annuals. So I spent so much time working on this thing and getting it built. I hadn't maybe ordered seeds or anything, and so I just planted what I had laying around from the past. So I planted a few tomatoes out here. I started the seeds indoors January 2nd. I think I put them in the ground. It was in February sometime. So actually these tomatoes, this picture I took on January 4th. So if plant birthdays are when they're put in the ground, their germination day, it was their one year germination day birthday, was January 2nd. So they're over a year old. Some observations with these guys. They were still healthy and producing at a year. I've seen that when I got to mid-December, I set the thermostat down to at 40 or 45. They didn't ripen anymore. These probably aren't the best varieties either for that, because they're just what I had laying around. There are varieties that are more cold season growing. But probably the biggest issue I actually seen with them was during the late summer. It was getting too hot, which is really why I opened the bottom vents, because they were cracking quite a bit. So if you're doing market tomatoes, that's a pretty bad thing. I was using them for just dehydrating and stuff. Not really as big a deal for that. But definitely when you're doing greenhouse growing, you want to look at varieties that are meant for greenhouses and stuff. I didn't know what I was doing at all with vine management when I planted them. I thought I was growing tomatoes outdoors in a garden, and it's totally different how you trellis those. So I'm planning to plant some new ones here outside in the greenhouse probably in a couple of weeks. And I was running the cables and setting up more commercial style vine management systems with the little spools and stuff. I kind of ended up adding it on the fly at the end after they were too big, which was kind of a pain. You kind of see the chaos of vines I've got here that I had to deal with because I wasn't prepared. And then definitely if you're growing in a greenhouse, look for grafted greenhouse varieties because they'll be more robust and you won't have cracking issues and other things as much if you're selecting for that. Any other questions on tomatoes? Some of the other things we tried, more vegetable related, radishes. This is actually from the ladder looking down. These are lettuces. These were awesome, especially with the COVID situation this year. It was awesome to be able to pick your own lettuces. Lettuces were great. I had these purple cauliflowers. They did really well. I made really beautiful cauliflower. The black broccoli I'd say was average. My Brussels sprouts were not good at all. I think by the time they were of age that they should be producing Brussels sprouts, it was already too warm for them. So they never actually produced Brussels sprouts. Some other things, other vegetables, turmeric, they did okay. They ended up getting kind of shaded out by some peppers I planted later on. Turmeric is definitely something we can't grow here normally. Things I do differently with these, I would start my brassicas sooner and probably not go for Brussels sprouts. So that's what I did this year. The cauliflowers, we eat quite a bit of cauliflower. They're doing really nice already. So they'll be ready sooner than these guys were. Then with the lettuces, there's a lot of folks, like if you're doing the deep winter greenhouse stuff, that's really, they don't grow in the ground. They have a rock bed heat storage system in those, so you can't grow in the ground. And so they usually will use gutters to plant the lettuces in. And I thought I'd give that a shot to see how it works. And wife really likes it because the lettuce is clean. You don't have to wash off dirt and bugs, or I have a lot of toads out there. You don't have to chase the toads out of the lettuce when you pick it. So it's nice. That's kind of some of the vegetables. I've got these apocalypse scorpion peppers. These guys have done awesome. I didn't know that peppers were a perennial when I planted them. I had let the kids pick seeds out of the seed catalog, and they thought these looked cool, I guess. These are some variety of super hot pepper. So we don't eat them, but I actually found a pretty good market for them locally for folks that make hot sauce and stuff. So they did really good. So they're still doing well. From what I understand, they'll typically live 5 to 10 years. I don't know if I want them in the same spot for that long, but it's been cool enough now. In late December, they've had a lot of leaf drop and stuff, just going a little bit dormant, and they're actually starting to come out of it already with our lengthening days. But they've actually still had peppers on them, and I picked a good number of them a week ago. I expect to have maybe a month of probably from now forward that it'll take for him to start setting new ones. Moringa. I don't know if anyone knows moringa, sometimes called the drumstick tree. These are a tree that's very popular in Africa, India, the Philippines, and you eat the leaves. They are very super nutritious, known as kind of a superfood if you live in a poor part of Africa or wherever, where you can eat these and get a lot of the nutrients that you need. So it's really good for folks that might not be able to afford meats and some other more expensive foods. But I found local Filipino folks are really excited that they could get this fresh. Usually we can just get this in the foreign grocery stores, might have it sometimes, and if they do, it's frozen, which is a lot different than fresh. And this guy grew super vigorously. He actually, I cut it back down, but he was about 10 foot high. And it's supposed to be a dwarf variety. I got some super dwarf bananas. Grew cucamelons, they're called. I'm not a big fan of them, but I got a plant for free. They're really a variety of cucumber. One of the big things you have to watch for if you're growing in greenhouses like this is pollination. And I find it's hard with a lot of unusual plants to find information on how to pollinate them or how they pollinate naturally. So these guys, they would need to be hand pollinated if you actually like them and want a lot of them. I had enough insects during the summertime. It seemed like there's some moths that like to pollinate them, so I didn't get maybe as vigorous or fruitful harvest as I would have if they were outside, but they definitely grew vegetatively well everywhere. But not something I'd do again because I don't really like them. Monstera deliciosa, or sometimes people grow these as house plants. I call them Swiss cheese plants. Their fruit's incredible. I don't know if anyone in our group has had these. And if you're from Florida, you might get to have these sometimes, but they're really good. Passion fruit. I got passion fruit vines. And that's one of the things that I really like, eating passion fruit out of hand. And they can be really expensive for us to buy them around here. Black sapote, they look like this. I start a lot of trees from seed and sell seedlings and grafted ones online. So black sapote is one of those that I do. I don't remember who was describing it for us. It's sometimes called chocolate pudding fruit. It's got the texture of chocolate pudding. It does not have the flavor of it. It's pretty mild flavor, not much to it at all. You cut it open, eat it when it's very soft and mushy like this. They're related to persimmons and grow in a similar manner. Patangas, or Suriname cherries. Got a few of those. That's one that I had on the plant. Canistel, or egg fruit, and toads. That's the tree in the background here. They produce a fruit that's it's yellow inside, just like an egg yolk, and it has the same textures like a hard-boiled egg yolk. It's kind of crumbly, not very flavorful. It's usually best to make it into a smoothie or something like that. We can add some more flavorful things to it. That's that guy. He's doing really nice out there.
Your canistels and your black sapote will be more flavorful if you get them in the selected varieties.
Yeah. These, mine are definitely not old enough to fruit. And before I had the structure, I definitely would never have the chance to grow them to a size where they could produce. I don't have any grafted ones of those yet. This loquat here is one I started from seed and then grafted on Big Jim variety, which is one of the more popular ones for eating for fruit. Caracuelo or Garcinia madruno. Longans. I was neat to see the new growth on these. Has this beautiful red, pinkish color to them. They're doing pretty good in pots. I don't have grafted versions of those yet either. But yeah, if you're in Southern Florida, you guys are able to grow these, Southern California. And my favorites, Annonaceae. This was mentioned by one of the fellows, one of our previous ones. He mentioned that Annonaceae, some of these do well in pots, and they'll actually fruit in pots, which is maybe part of why I like it. The other reason is they're just super delicious. Maybe the most widespread thing that's similar to these that folks would know would be pawpaws. They have a similar white texture inside to them with the same black seeds. Cherimoya is what I've got here. This is I've got one that I put 5 different varieties on, and got my first blossoms this year. But not enough blossoms to pollinate, but got to see them and smell them. I do a lot of soursop, some mountain sop. Mountain sop are usually best started as a rootstock for others. They're not that great to eat. Sugar apples, or known as squamosa, and then the atamoyas, which are actually cross between the sugar apple and the cherimoya. And I got some of these guys, the bullock's heart, which are mostly neat for their coloring and shape. They're not. I don't think they have quite as good a flavor as a soursop or a cherimoya does. Let's see. Oh, a few other things. Narhangilas. These guys are a solanum, so related to tomatoes, but I haven't had any ripe ones yet. This is actually a picture of the one that I had outside the greenhouse. It took me a while to figure out how to hand pollinate these guys. You can kind of see that's why I threw in this picture here. The pollen is within them. You can't just use like a paintbrush or something. You gotta actually pluck these guys off, and you just tap them a little bit, and the pollens come out. Then you can put that onto your brush and then pollinate the pistils of the flowers. Then they'll set fruit nicely. I have some now that are just starting to turn yellow. What I'm told is they taste citrusy, like a sweet citrusy fruit. So we'll see. I have a couple white sapote that I grafted on. This is a white sapote. Folks might know what that is. So that's what I got in the presentation. Any other questions?
So if anyone has any questions, go ahead and unmute. You can ask, or if you want to put something in the chat, you can also make comments in the chat, and then Shannon can review those at the end if you'd like. That was a great talk, Shannon.
Yeah, thanks.
So much information. It's great.
Yeah, hopefully it wasn't too much, too fast, too deep.
Great.
Most of the stuff in pots, or is it actually in the ground, a lot of it?
Yeah, most of the trees and stuff I still have in pots. I'd like to put them in the ground, but I just haven't convinced myself I know where I want to put them for the long haul. So I still have a lot of them in pots.
And Shannon, are you concerned at all if you do put them in the ground? Will the roots get into your ductwork?
That's a good question that I've kind of wondered about. But I suspect that it would behave similar to self-pruning pots, where because of the airflow in there, the roots aren't going to go into the tubes.
Okay, thank you.
Shannon, what would you change if you build another one?
Oh, I'm an engineer. I'd probably change everything. I think the structure, there's a lot of things I would change with the structure. I kind of mentioned the lower vent doors. I would get rid of that knee wall on the south side because it does reduce the amount of light that I get onto the floor. As long as you're growing taller things, if you're there in pots or on tables, it's not a big deal. But I found like when I put lettuces or radishes or other things on the ground, they're not going to get as much sunlight during that winter time. I didn't know how much cooling I could get from the top doors and from the climate battery, so I didn't want to risk that. But I'm debating maybe this summer if I have time to actually remove the knee wall and then just use a shade curtain over it for the short period of time I might need that. The other thing too with the top vent doors, instead of the clerestory style roof where it extends above the peak of the glazing, I would probably bring that down and do doors that flip open on that north roof instead of having it on that vertical wall. I did it this way because I was just concerned about snowfall and I wanted to make sure that they could always open and close if they needed to. But I think that would be an improvement. Mostly because it's not that fun to be on a 20-foot ladder up there doing maintenance or latching and unlatching them the couple times I need to. And you're not growing anything up there. You're just having extra heat loss that you wouldn't necessarily need from that shape of the structure. With the climate battery and stuff, I want to go through the data more yet in some of the simulations to see like what exact things I'd change. It's been pretty good, but I'm sure there's some areas of improvement there too. One of the bigger questions I have with it is like, what's the right tube spacing? So I've seen some papers with good data that were much larger tube spacing than I've got. And you really want to get your tubes as close together as you can because you can capture more of that heat faster and you could get by with less airflow, lower speed fans, but you displace, there's a trade-off, right? So understanding that trade-off, I think would yield something in between, something less, I think, than the 2-foot that I have now.
Cool. Thanks.
How much flow are you getting from just direct radiation up out of the earth and then conduction in your growing beds?
Yeah, that's a good question. I'm not quite sure if I have the right data to quantify that. So I don't know. No. A lot less than is coming out of the tubes.
Cost?
I did probably way too much of this myself. So my costs are all mostly materials, which was less than 20,000, just under 20,000. I think for the above ground structure, I think there's a lot of opportunity. Changing that north structure would reduce the cost. One of the things I like with the new deep winter greenhouse style is a simpler assembly and lower cost north wall structure. The glazing material that I have is a triple walled polycarbonate, so it's pretty well insulated and it's fairly expensive as far as those go. But you don't want to lose that heat because then you'd have to have more backup. I think there's some opportunity to look at the curtains, the automatic curtains. Because if you could get one of those that would work reliably, you could go with a lower cost glazing material. So I think there's some opportunity there.
How about your cooling and heating transfer? Isn't water more efficient than air?
Water, I don't know if I use the word efficient, but it can transfer more faster. But you would still need to, in order to use water, you would need to move your heat from the air to the water, from the water to the ground. So it would be more complex, because so that you'd need to have a fan with a radiator to blow over the radiator to conduct it to the water lines. That is something I've seen, like as an additional heat source. You can put hot water lines or a hot water radiator on the tubes of your climate battery, and so you can increase your temperatures of your air with a little bit when you need to with that kind of system. So that's, people will do like just a hot water heater like you might have for your house, heating the tubes for small quantities. I've seen people doing that for if they're doing starter plants, they'll put PEX tubes under their growing trays with the hot water heater and heat just the pots.
Did you start from scratch, or did you have plans for this?
I wouldn't say I probably had really any plans other than the CAD models I drew up. I've referenced any research papers or other documents out there I could find. There are some companies that do design this kind of stuff as a service for you. Probably one of the most famous and most ridiculous expensive ones is Ceres out of Colorado. They were really big into designing these for people. They still do, but a lot of what they're designing now is structures for marijuana growing.
With as much as you've managed to get climate bending out of this, you need at least 4 times as much space with all the things you can grow there.
That's the number one problem. You're right. That's exactly right. Yeah.
So why did you go with the more exotic tropicals instead of something simple and delicious like mangoes?
Well, like Javier mentioned, mangoes don't do well in pots.
But you can plant it in the ground there. You should be okay with it.
Yes, I can. But I've been growing trees for years before I had this. So, a lot of these plants are not just 1-year-olds. They've been there for a little bit longer. At least been in a pot. But I can get mangoes in the grocery store. I cannot get an Adamoya in the grocery store.
You can't get a good mango in the grocery store.
You're right. You can't get good ones, but you can get them. People know what they are here. They don't even know what these other things are. There's so much more food we could be eating in the world.
Shannon, does that 30-foot depth for a year-round stable temperature in the earth hold true everywhere, or is it just that deep because you have such large temperature swings up in South Dakota, and so it mitigates as you go into a more milder climate?
Mm-hmm. Yeah. I think that the second graph that had those curves, your annual temperature swing is going to be less. But I think that depth thing is still generally true. That when you get down there, it's pretty constant year round. But your upper swings are going to be less farther north. If you want more data on that, there's tons of info out there for geothermal engineering purposes. A lot of that data is used for the waterline type systems, where you'll dig big trenches and you'll coil the PEX style water tubes in that, and then run that to a heat exchanger to bump it up to heat your home or your other structures.
So that's tending to be thermal battery as well when they do that, not just pulling heat out, but also pumping heat in and when they're cooling in the summer.
Yeah, if you're using it for cooling in the summertime, it would be a sort of battery. I differentiate because you're not intentionally trying to do that. You're not trying to insulate it and hold that energy there in any way. It's still going to dissipate out.
I'm interested in doing a cooling battery for a walk-in and freezing a huge block of ice right underneath your refrigerated storage. There's a guy in New England that was doing year-round with just for a refrigerator, and he could do that with a Freon loop that radiated to the night sky to freeze ice in his refrigerator and run the thing year round. But I want to scale it up to where you can do, for a small storage for a farm, 1,000 bushels a year, maybe, that you could cool. And I think it's workable to do that. That's one of the biggest energy uses on a farm is refrigeration for storing stuff in the summertime.
Mm-hmm.
So since that water method of heating and cooling has been established and around for years, how come you just immediately gave up on that and went to using the air to the battery?
Sure. The main difference is the cost, the complexity of the system. So if you're doing well-based geothermal or the other ones, you're not using. It's not direct use. They're taking that water and then it's flowing through a heat pump to up the temperature, because 45 degree water doesn't give you a lot of heating. So it's a lot more expensive. I don't know, for reference, I did look at that kind of stuff for my house. And usually they want to drill wells so that they can get it down in that 30-foot range. Just $30,000-$40,000 just to heat my house. It's a big cost difference. It's super cheap once you get it built, but it's not a low total cost of ownership.
You have one moving part versus lots of moving parts.
That's right. You have a lot more stuff to go wrong. And it's a lot harder to get to fix when you when you have a tube break underground.
Yeah, you're just literally a drop in, drop a new fan in and you can go.
Yeah.
All right, so this will be this is recorded, and it'll take me a couple days to get it up and emailed out to people. But you'll be able to come back and look at aspects of the talk if there's something you want to go back and